Koertland Beyer has been with us for several years. Koertland's got a background in chemistry, was in the medical field for a while. We brought Koertland on board to help us understand water quality and a lot of the chemistry that's happening in the water. So Koertland's going to give you a little bit of a taste of what chemistry is doing in irrigation water, and then we'll do a quick demonstration to show you what that looks like visually.
Yeah, thanks, Kurt. So a lot of times we look at water, and if you look at these 3 jars up here, it's clear, and you don't see all the stuff that's in them. Water really is a complete ecosystem. There's biology in there, and there's minerals, and there's just a lot of life. And so the first thing I'd like to talk about here is when we pull water out of a pond or out of a well, what is it? Where does it come from? And why are waters so different? And so this picture does a good job of showing when we get some rain, that's going to come across different types of soils and flow along creeks and streams and filter down through sand and gravel. When it falls, it's nearly distilled water. And so that water wants to take on stuff. And so whatever it goes through, it's taking that on. And so if that water goes through a limestone aquifer, it's going to take on limestone. If it goes through some gypsum, it's going to take on gypsum. And so by the time that water gets down here and settles in its home, it's gone through a certain amount of minerals and whatnot, and now it's sitting in a place and it's taking on whatever is in that environment. So when we go poking a hole down here, that's the water that we're getting, right? And also, as we pump our water, we get this cone of depression, and that's where this water is coming from usually. Now, having said that, an aquifer, or the sand and gravel that we're pumping out of, isn't necessarily this equally distributed same size of rock or whatever everywhere. And so sometimes water can be coming from one way versus another way if the one side is a little tighter than the other. And so after we've been pumping for most of the summer, the water that we can be pumping from late in the summer could be coming from somewhere else underground, and so the water can actually change on you. And so that's one thing that we need to keep in mind. And while I was here on this picture slide, I just wanted to mention that. I know most of you guys can't see what's going on here, but this is a standard subsurface irrigation water sample. We test for 14 different minerals, and this helps us get an idea whether this water is going to need a little help or not. That's what a standard water sample looks like. And within the water, there's good stuff and there's bad stuff. And of course, the good stuff is the things that your plant likes, nitrates, potassium, boron, calcium, sulfate. The environmental people don't necessarily sulfate and nitrate in their water, but as farmers, we do. It helps our plants grow. And then, of course, the bad things that we don't want, sodium, of course, iron and manganese. And those are nutrients, but in a drip situation, they can cause plugging issues. Iron bacteria and bicarbonates, and they're also components of plugging that we have to deal with. So I'd like to talk just briefly about the 2 different branches of water quality. First of all, we have an agronomic water quality. This is what affects our plants and helps our plants grow or not. And the other one is going to be this risk of plugging to our emitters. And the emitter here that's on your right, this is a high manganese water system, and again, I'm sure you probably can't see it, but this little path of undulation here has got some plugging going on. So I'll talk first about keeping your lines clean. And the minerals that we're looking for here are the iron, manganese, bacteria, and then we're also going to be looking at bicarbonates because they complicate the problems. Iron and manganese, both in the well, live in a +2 ionic state. And because of that, they are soluble in the water. Just like that clear water over there, you could have iron and manganese in that water. And matter of fact, I think we do have some. And you can't see it because it's in solution. But as that water comes to the surface, it oxidizes because of bacteria. Bacteria do this. And also, just because now there's oxygen present. And when iron and manganese oxidize, they go to a +4 state, and that causes them to come out of solution and puts them in suspension. And now because they're in suspension, they can just fall out. And if you've got water that when you fill it up at the sink and you set that glass on the counter and you come back a couple hours later or the next day and there's a layer of red or orange or brown stuff in the bottom, that's because that iron and manganese has precipitated. And that's what will plug up your drip tape. And so what we're looking at here is, in this picture, is a drip tape that's started to plug a little bit with an iron kind of bicarbonate mix. And so when we look at the water sample, we're looking for iron levels that are above 0.3 parts per million, manganese levels that would be above that 0.115, and then whether bacteria is present or not. Those are the kind of the thresholds that we're looking for. Now, as far as the nutrients are concerned in water, one of the biggest issues that guys will face is when they have high sodium in their water. And we're looking at 50-ish parts per million and above. Because of the nature of sodium, it decreases the availability of water. So sodium likes to take on water. Sodium can attract about 3 molecules of water for every molecule of sodium. And it makes it difficult for the plant to pull that water away from the sodium. So even though there might be water in your soil, it makes it hard for your plant to extract it. And also, sodium reduces soil permeability. So the soil doesn't want to give up the water, and usually those sodiums are holding on pretty tight. And high sodium soils or sodiac soils tend not to percolate very well, and so you get runoff during bigger rain events that you wouldn't otherwise get. Once that sodium gets in the plant because of mass flow intake, sodium looks a lot like potassium to plants, and it tries to create molecules around a sodium, and it even can in some cases. But of course, whatever that structural component is that the plant's trying to make, it doesn't function correctly because it's got a sodium there instead of potassium. And then one of the main problems is that sodium interferes with nitrogen uptake, and that occurs in the soil. The next one that I want to talk about here is bicarbonates. The picture that we've got up here is just a map of the United States. It's a regional map for hard water or bicarbonates that are found in the water. Hard water is all over the United States. A lot of it's concentrated in the Midwest here. And hard water is either calcium or magnesium bicarbonates. And bicarbonates are really an issue for us because bicarbonates like to tie up cation fertilizers. And so when we put water on our fields that have bicarbonates in it, for every pound of bicarbonates we put in, we're potentially tying up a pound of cation fertilizer, whether that's ammonium or zinc, potassium, any fertilizer that's got a plus sign associated with it. And that makes it difficult for the plant to pull that off of that bicarbonate. They usually come associated, again, with the calcium or magnesium, but there's an ionic exchange that occurs, and that's what we're actually going to do with the water here today, is we're going to do a double replacement ion exchange and show you what happens with that. So this whole issue of bicarbonates came to our attention several years ago when we had a good year for rainfall. And a couple miles north of here, adjacent to our drip field, we've got a pivot field. And this is a partial map of that pivot. And I'm going to just draw the circle of the pivot here. And you can see that the inside of this pivot produced less yield than the outside of the pivot did by as many as 20 bushels an acre. And we contribute this to the bicarbonates that are in the water. And as they build up, they rob the nutrients from what we put in. So there are some solutions to taking care of the issues associated with water. Iron and manganese can be mitigated with acid or a sulfur burner, because we can oxidize those minerals prior to them hitting the filter, and then we can filter them out. And then there's also other agents that we can use to sequester them or keep them from oxidizing while they're in the drip tape so they don't cause problems. Sodium or salt has to be leached from the soil. Once that gets put on, it's got to be drained through. And the way that we can assist that is by putting gypsum on our soil or treating our water with sulfuric acid or using a sulfur burner. That sulfur likes to hook up with the sodium, and that'll help that to leach faster. And then the bicarbonates, the solution for bicarbonates gas off when they come in contact with an acid or something that's a lower pH. And so that they actually turn into water and carbon dioxide. When that happens, it's an acid-base reaction. Bicarbonates, they can leach just like sodium. It's a slower process, but that's naturally how that would happen by adding gypsum or, again, acidifying our water, whether that's with a sulfur burner or some type of acid. Those would be the solutions there. This is a group of sand filters here, just to illustrate the oxidizing and filtration. So an oxidization agent is added shortly after the well. That oxidization agent, such as chlorine, is mixed with water, and that oxidization process completes, and then it hits the sand filters, filtering it out, and then that just stops that from going into the system. This is a picture of a sulfur burner. And again, these remove bicarbonates by lowering the pH, and the calcium carbonate that comes into the machine leaves as calcium sulfate, which is gypsum. It's a fertilizer to us. That sulfate becomes available for the crops. And the sulfate, and there are some sulfate ions also assist sodium leaching from the soil. And then over the last couple of years, we've been doing some research adding anhydrous ammonia and being able to use anhydrous ammonia in our irrigation water, which wouldn't be possible if we weren't acidifying it. It's another option that you have when you have there. Just another quick slide here of sulfur. One of the things that we often miss is the nutrient sulfur. And over the last, 10 years, 20 years, we don't really have a whole lot of sulfur falling out of the sky anymore. When we were burning diesel fuel that had a higher sulfur content and we had acid rain, that acid was sulfur content. The rain was cleaning that out of the sky and it was falling on our ground. And because of that, we had an adequate supply of sulfur. Having said that, we don't anymore. And so one of the things that we're finding is that a lot of our growers are short on sulfur. And so it's a nutrient that we need to add. The benefit of having a sulfur burner or acidizing your water with sulfuric acid is that you're adding that sulfur component to your soil every time you irrigate. We look at this graph here, we can see that about the time that we start irrigating, say V6 or V8 maybe here, that's when this graph really starts taking off, or that's when the plant starts really needing a lot of sulfur. And we can provide that sulfur through a sulfur burner or through sulfuric acid injections. So this is just one way that you can do that. I just drew a line there at about 500. A sulfur burner, sulfuric acid, these are significant investments, and with the payoff of keeping your ground in a situation where you're not building up bicarbonates and having those yield losses. So I've just put together a cost comparison of sulfuric acid using AMS and a sulfur burner over the period of 10 years. And you can see here that in the totals, the cost per acre over the course of 10 years is about $140 an acre with acid, and so that's cost prohibitive. Most people who find themselves in a situation where they need to acidize end up with a sulfur burner, bringing your cost down to about $38.13 an acre, as opposed to that $140. And with AMS, if we were going to do the same thing with AMS, it'd run us about $62.50 an acre. What we'd like to show here, does anybody have any questions about that? I think we're going to go ahead and go into this demonstration there. So basically what we've got set up here is a jar test. And this is just our office water, isn't it? Yep. This is just our office water here. The bicarbonate count's about 275, I think. And we're going to add some 1034O, which is is known to cause a reaction. This would be like what a typical jar test would be. So as we add this 1034O, the water is going to get cloudy because there's a double replacement reaction that's going on. This is not only going to plug your drip tape, but the nutrients here are being tied up. And so this fertilizer, the cloudy stuff that you see now is tied up fertilizer. So if we acidify the water with some sulfuric acid, and then and let those bicarbonates leave the water, and then we add, okay, and again, we're going to want that somewhere in the 6.0 pH range. Yeah. Okay, yep. Oh, yep, that'll take care of it. And then we add some of this 1034O. You can see that reaction doesn't occur because the bicarbonates are no longer in the water. And then in this last sample, we've got a fertilizer that is an acidic base. I believe they use phosphoric acid as the base of the fertilizer. And again, because the water has been acidified by the fertilizer itself, that reaction doesn't occur. One of the things that that I think that we need to talk about more, that we're not talking enough about, is the quality of our water, not just what we're irrigating, but also with what we're spraying, because we tie up a lot of nutrients when we spray with water that's high in bicarbonates.
We get a lot of questions about what kind of fertilizer you can run, and this is a demonstration of if you did this and you were going to use this fertilizer, we would say don't do that. If it turns cloudy, turns white, settles out over time, that's a bad reaction to see something like this, because that will plug up a drip system. It will actually plug up a center pivot as well. So you can see, so one of the standard things is do not use 1034O through a drip system. You could do it if you acidize your water first. Mm-hmm. But so this fertilizer, this dry powder we put in here it's an ICL product. We've got a few pallets of it sitting back here. Just in the last couple months, we've started carrying that. So that is something we're going to have available going forward. It's basically a way to acidize your system using the fertilizer. So as you fertigate, you're going to be cleaning your system, and that nutrient is very plant available. So we've got some good tests going on out here on our ground this year, and we'll have some yield data to share as well. That ICL product also makes a really good starter fertilizer, especially for those who have high pH soils. Using an acid-based fertilizer as a starter is a really good idea. So you would solubilize it and make your own fertilizer. So essentially just a tank of water, dump the fertilizer in, agitate it, and run it as a starter or through your drip system. Yep. So for example, Galen did a couple applications out here, took a 1,500 gallon tank. I think we put in 2,000 pounds of dry fertilizer into 1,500 gallons of water and then fertigated with it. And we can help with the analysis and figuring out the ratios and what you're looking for. And the cost, so just 1034O obviously is the cheapest source of phosphorus. The ICL fertilizer is going to be 30 to 40% more. The next step up, though, would be your liquid products like a Nature's, Conklin, AgroLiquid. All of those are going to be really high dollar, but they're doing something similar. So basically, by buying it in a dry form, you're cutting the cost in about half. So what we're seeing.